Good morning, one and all. My name is Andur Garo from EC Department, Vignans Nirla. Here we'll discuss the Unit 3, that is the sampling process. After that, we'll see the sampling theorem. First, the introduction to the sampling process. The sampling process, as the name, itself suggests that it's a process of converting a continuous time signal into the discrete time signal. Process of converting a continuous time signal into the discrete time signal. Generally, the naturally encountered signals are nothing but our continuous time signals, but most probably we'll use the discrete versions in the computers in any updated systems like that. Hence, we need the conversion from the continuous time signal to the discrete time signal. The process of converting that continuous time signal into the discrete time signal is nothing but our sampling process. Basically, this sampling process can be done by using a switch connection, that is a mechanical switch or an electronic switch will be used. Practically, we'll use this electronic switch, but if we consider in the form of a particular switch operation, for that consider a continuous time signal like this, which varies with respect to the t. I am considering a sinusoidal signal like this, which is being represented as x of t. X of t varies with respect to the t. That means for all the values of the t, there is a particular value. With respect to the t, for all the values of the t, there is a particular value. That is nothing but a continuous time signal. And this continuous time signal will be given to a one particular switch connection, that is x of t is being given to a one particular switch, and this switch will be operated for every ts seconds. For every ts seconds, the switch will be operated for every ts seconds, and this particular ts seconds, the switch will be closed for every ts seconds. In between the ts to the 2ts, for example, initially the switch will be closed at t is equal to 0. The switch will be closed. Again, the switch will be closed at t is equal to ts. In between these two times, the switch will be said to be as an open. And again, the switch will be closed at the 2ts, like that. Like that, the switch will be operated. And for example, if we start at with the t is equal to 0 closed switch, at that particular positions, how we'll get the discrete time signal is, at t is equal to 0, we'll take up the particular signal, continuous time signal. At t is equal to 0, the switch will be closed. Therefore, x of t value at t is equal to 0. At x of t value at t is equal to 0 will be produced as our output of the switch. That is x of nt value, which is nothing but x of nts, which is equal to x of xs of t. That the sample version at t is equal to 0, this particular sample will be produced as our output. That means this particular value as 0 at here, that 0 will be produced at here. The same 0 will be produced at here. Next, again after the t is equal to 0, the switch will be open. That means it will not pick up the values for a particular duration. It will not pick up the values for a particular duration. After it encounters the t is equal to ts, the switch will be closed. Therefore, that particular peak value or the amplitude of that particular sinusoidal amplitude will be picked up. That picked up one will be produced as our output. That is the new sample at ts units. The first one at t is equal to 0, second one is at t is equal to ts. Again, after the TS, up to the 2 TS, the switch will be closed. That means there won't be any sample at the output. Again, we'll pick up one more sample at here. At here, 2 TS. 2 TS, we'll pick up a sample. Again, at the 3 TS, we'll pick up the another sample like this. That sample will be produced at here. Again, at 4 TS, we'll pick up a sample. We'll pick up a sample. Next, at the 5 TS, we'll pick up the sample. As the peak is in the negative, we'll get a negative sample at here. We'll get a negative sample. Next, at 6 TS, another sample. At 7 TS, another sample, like that. This is the 7 TS. We'll pick up the another sample. Next, the 8 TS, we'll pick up the another sample. Next, at 9 TS, we'll have the another sample. At the 9 TS, the value will as the 0. The 9 TS, the value will be the 0. 9 TS, the value will be 0. This is a continuous time signal which will be converted into the discrete. That means it is defined at TS locations. This is a TS, this is a 2 TS, this is 3 TS, 4 TS, like that. That's why this is nothing but our NTS. When n is equal to 0, that is the first one, n is equal to 1, second, n is equal to third, n is equal to 3, fourth, n is equal to 4, fifth one, like that. This x of n, which is nothing but our x of NTS, which is nothing but our sample version, xs of t. That what we will get, how we will convert a continuous time signal into the discrete time signal. For the how many number of samples that will be taken, that many number of samples will be produced as our output. This is generally a mechanical switch connection, but in the practical cases, this particular switch can be a transistor, diode, or MOSFETs, like that. That process of converting a continuous time to the discrete time signal can be performed in the by using the simple switch connections like transistors, resistor, and transistors and diodes, etc. Okay, this is the process of converting a continuous time signal into the discrete time signal, sampling. As I have explained that the switch connection for getting the discrete time signal from the continuous time signal. These are the points what we have discussed, that one. Then generally the switch will be closed for a very short interval of tau. That's tau generally it is been 0. Tau will be 0. Ideally the case as tau is been 0, and the sample will be picked up for every t seconds, during which will have the availability, the output will be present. When we take the continuous time signal x of t as an input and xs of t as an output, the xs of t and x of nt and x of n, which is nothing but our output sample signal. And here is a continuous time signal x of t, which has been converted into the discrete version like x of n. After the sampling, the signal is being defined as a discrete time instance of time, and the time interval between the two successive samples, we have seen it as the TS. That is, the first sample is at t is equal to 0, the next sample will be at TS, and the next sample will be at the 2 TS, and so on. Then a sampling frequency is being given by the Fs is equal to 1 by TS. This sampling frequency is nothing but at what range of frequency the switch will be operated. that particular range is nothing but our sampling frequency. The sampling frequency will be defined as 1 by Ts, which is nothing but the sampling. TSC is nothing but the sampling interval. It is the interval where between the two successive samples. Generally, if we take the initial value, it's from 0. The next sample will be at Ts, and the next one is at 2 Ts, and the next one at the 3 Ts. Therefore, the sampling interval will be nothing but the Ts minus 0, or the 2 Ts minus Ts, or 3 Ts minus 2 Ts, or 4 Ts minus 3 Ts. Generally, it will be given as Ts only, right? Hence, this is the process of converting a continuous time signal into the discrete time signal. Next. Now the sampling theorem. Sampling theorem is the process where we will consider a continuous time signal which has been sampled into a particular discrete time signal. Then after the sampling process, again we need to recover the continuous time signal from the samples. This entire process will be defined or been stated in a particular statement called as the sampling theorem. That means a continuous time signal can be represented in its samples and can be recovered back. When the sampling we recovered back means, that means we can get the continuous signal back when the sampling frequency is being greater than, that say Fs will be greater than or equal to 2Fm. When this particular condition only, the continuous signal x of t is recovered back. Otherwise, if for example, what is the other choice is, if the Fs is less than 2Fm, then the x of t is not recovered. Is not the recovered case. That is the statement. If this is the case, that is Fs greater than or equal to 2Fm, then the continuous signal will be sampled. Again it will be get back and the reverse process will be easily done. Therefore we'll get the continuous time signal. If the x of t is not recovered, then that will be the case of Fs will be less than 2Fm. For example, consider the signal x of t, which is nothing but a continuous time signal. What we have initially considered is continuous time signal, and then take the Fourier transform of this particular one. Let it be the Fourier transform of x of t as x of omega. This x of omega is to be band limited. Then only this reconstruction process will be done effectively. Recovered process can be done effectively. Now we'll see that x of t and x of omega like this. Let us consider the continuous time signal which is being given as like this. The same sinusoidal signal I am considering it, which varies with respect to the t and is represented as x of t, which is a continuous time signal. Now the Fourier transform of this particular one, as our x of omega, which is represented with respect to omega, as x of omega we are considering as a band limited. It's as the band limited. Therefore it will be defined like this, as a one particular rectangular function with the highest frequency component as Wm and minus Wm and plus Wm. Okay, that means this particular triangular function will says that that beyond this Wm there were the frequency components values will be the zeros, and beyond this minus Wm the frequency components has been 0. That means whatever the frequency components of x of omega will be band limited up to the Wm, where Wm is the maximum frequency component. Maximum frequency component. It's the maximum frequency component. The Fourier x of t whose Fourier transform as x of omega, which is x of t, this is a continuous time signal. Consider its corresponding Fourier transform representation as x of omega, which is a band limited. That means there won't be any frequency components other than that of Wm, and below this Wm only we'll have the frequency components. Those frequency components will be represented as the triangular function like this. This continuous version, then their corresponding Fourier transform representation or frequency domain representation as like this. This is the basic thing, the continuous version and their corresponding Fourier transform representation. Next we'll see how we'll get a discrete time signal. Next one is converting that discrete time signal, taking their Fourier transform, and again getting the spectrum of that Fourier transform and giving the 3 different cases. That process will use our sampling process. Process can be getting by multiplying the 2 signals, like that's generally the first one is the continuous time signal will be multiplied with the train of impulses function, and we'll get the sample signal x of n. How we'll perform this particular one is, consider as a continuous time signal as this. Consider the continuous time signal. Then it will be multiplied with the train of impulses function, like this. For example, if we consider the continuous time signal here, then consider a train of impulses function. This is x of t. Then the train of impulses function delta t of t, which is nothing but it will have the samples from which will be separated by a distance of ts. That means first sample will be at 0, next to ts, next 2ts, 3ts, and the 4ts, like that. This is 3ts, 4ts, 5ts, 6ts, and so on. Similarly, we will have in the negative side also, that's minus ts and so on. Simply multiply these two, that's x of t multiplied with the train of impulses function, will get the discrete version. That means here the value as 0, initial value of the continuous signal, will be multiplied with this impulse. Therefore, we'll get a signal like this. That means 0 into 1 will be the 0 here, that the sample will be the 0. Next, at ts, whatever the sample at here, that will be multiplied with this one. Therefore, we'll get a sample. At 2ts, whatever the sample at here, that will be multiplied with 1. Therefore, we'll get another sample here. Next, at 3ts, the sample is at here. Like that sample will have produced like this. This sample will be multiplied with 1 here, and we'll get the sample like this. Next, the 5th one. Next, at here 0. This is for 0, ts, 2ts, 3ts, 4ts, and 5ts, and 6ts. This is nothing but our discrete version x of n, which is nothing but if we consider this discrete version as x of n, which is equal to x of t delta t of t delta t of t. Let us consider this multiplication of the two signals. Therefore, this one as our discrete time signal. X of n is equal to x of t delta t of t. Where that particular initially we'll call it as the, for example, as y of t as some x of t into delta t of t in terms of the time domain. In terms of time domain, it is been considered as y of t is equal to x of t delta t of t. That represents our output. Next.